You will spend around 38 days of your life brushing your teeth. Not in one stretch, of course. 2 minutes in the morning, 2 minutes at night. It feels insignificant, automatic, routine. But here is what most people never realize. The paste you use in those few minutes is controlled so tightly that a single parameter drifting out of range can shut down an entire production line. Its thickness is measured in units thousands of times greater than water. Its cleaning strength is assigned a numerical score. Its chemical structure is scanned, verified, and approved before it is ever allowed near a tube. People think toothpaste is just mint, foam, and a white paste. What is actually happening behind the scenes is closer to a precision-engineered system where chemistry, physics, and real-time data all collide. And it all starts in a place that looks nothing like a bathroom. It starts with rock, sand, minerals pulled from the ground. Because toothpaste does not clean your teeth because it foams. Foam is mostly psychological. The real cleaning comes from abrasives, microscopic particles that physically scrub plaque and stains away. One of the most common abrasives is hydrated silica. It begins as sand, but by the time it reaches a toothpaste plant, it has been processed, purified, and engineered so that every particle falls within a controlled size range. Not approximately, precisely. Another common abrasive is calcium carbonate, derived from limestone. This is also calcium phosphate, which can be produced from phosphate rock. Historically, manufacturers even used animal bones. Bones were heated to extreme temperatures, often above 800 degrees Celsius, in a process called calcination. This burned away organic material and left behind mineral-rich ash that could be ground into fine particles. It sounds extreme, but the principle is the same today. You need particles that are hard enough to clean, but not so hard that they damage enamel. And that balance is fragile. To measure it, manufacturers use something called relative dentin abrasivity, or RDA. This number defines how aggressive a toothpaste is. Most consumer toothpaste falls somewhere between 30 and 150 on the scale. Above that, you risk long-term damage. Below that, cleaning becomes ineffective. So before anything else happens, abrasives are classified, sorted, tested, and nothing moves forward until those numbers are exactly where they should be. Every raw material goes through this level of scrutiny. Glycerin, which gives toothpaste its smooth texture and prevents it from drying out, must meet strict purity standards. Sorbitol, which helps retain moisture and adds mild sweetness, is tested as well. Even water is treated and filtered to remove impurities. Each batch comes with documentation, certifications, traceability records. If something does not match, it is rejected immediately. Because once production starts, you're no longer dealing with individual ingredients. You're dealing with a system. And systems are harder to fix. The materials are stored in controlled environments before they ever touch a mixing vat. Humidity is kept within tight limits. Around 45% is common. Why does that matter? Because powders behave differently depending on moisture. Too much humidity and particles clump together. Too little and static can cause them to repel each other and resist mixing. Temperature is also controlled. Stability begins before the process even starts. Then the mixing phase begins. Inside large stainless steel vessels, sometimes holding thousands of liters, the base of the toothpaste starts to form. Water is introduced first, then glycerin flows in from storage tanks, often through pressurized systems that ensure consistent delivery. The mixture begins to thicken as binders are added. These are substances like carboxymethyl cellulose or xanthan gum. They create the internal structure of the paste. Without binders, toothpaste would separate into layers. Liquid would pool, solids would settle. The product would become unusable. As mixing continues, abrasives are introduced. This is a critical moment. The distribution of these particles must be uniform. If they cluster, parts of the toothpaste become too abrasive while others become ineffective. So mixing is not just about combining ingredients, it's about achieving perfect distribution. This is where sensors take over. Temperature probes monitor conditions across the entire vat, not just at one point, but at multiple locations. Thermal imaging can be used to confirm that heat is evenly distributed. Why heat? Because temperature affects everything. It influences how ingredients dissolve, how they interact, how they stabilize. Too much heat can degrade sensitive components. Too little and reactions do not complete properly. Humidity in the surrounding environment is also controlled during the stage. Even though the mixing is enclosed, external conditions still matter. Operators watch data streams constantly, And then comes one of the defining properties of toothpaste: viscosity. Toothpaste is what scientists call a non-Newtonian fluid. It behaves differently depending on the force applied. It stays in place when undisturbed, but flows when squeezed. Its viscosity can reach around 95,000 centipoise. For comparison, honey is around 10,000. Water is 1. So toothpaste is not just thick. It is engineered to be thick in a very specific way. If viscosity is too high, you struggle to squeeze it out of the tube. If it is too low, it drips off your brush. So measurements are taken continuously. Adjustments are made in real time. At the same time, pH is carefully controlled. Most toothpastes aim for a pH around 7, neutral. This protects enamel and ensures compatibility with fluoride. Fluoride is one of the most important ingredients in toothpaste. It helps remineralize enamel and prevent cavities, but it is sensitive to the environment. If the pH is off, fluoride compounds can become unstable and lose effectiveness. So the balance must be exact. As the mixture stabilizes, advanced testing begins. Spectrometers analyze the chemical composition. They confirm that each component is present in the correct proportion. Rheology tests examine how the paste flows under stress. These tests simulate real-world conditions: squeezing the tube, spreading on a brush, moving across teeth. Because toothpaste does not just need to exist, it needs to behave correctly. At this point, the paste is functional, but it still does not feel like toothpaste. Now comes the transformation that people actually notice: flavor. Mint oils are introduced, but they are more complex than they seem. The cooling sensation comes from compounds like menthol that activate receptors in your mouth. This creates the feeling of freshness. The intensity is carefully controlled. Too strong and it becomes uncomfortable. Too weak and it feels ineffective. Flavor oils are injected quickly and mixed thoroughly to ensure uniform distribution. Colorants may also be added. Some toothpastes remain plain white, others include colored gels or stripes. Those stripes are not just for appearance. They require precise control during filling, with multiple streams of paste flowing simultaneously. Now the toothpaste looks and tastes familiar, but it is still not approved. This is where testing becomes even more intense. Chromatography is used to analyze the composition. The mixture is separated into its components and displayed as peaks on a graph. Each peak represents a specific substance. Operators examine these peaks carefully. If something is slightly elevated, it is compared with control data. Is it within acceptable limits? Does it match expected behavior? If not, the batch is investigated. Preservatives are also tested. Toothpaste can sit in a tube for months or even years. It must resist microbial growth the entire time. So test samples are exposed to controlled conditions. Control samples are used for comparison. If controlled samples show growth while test samples remain clear, the preservative system is confirmed to work. This step is critical, because a product that looks perfect on day 1 can fail over time if preservation is not effective. Finally, everything is reviewed together: chemical composition, physical properties, sensory experience. Yes, sensory testing is real. Trained evaluators assess how the toothpaste feels, how it spreads, how it tastes, even how it foams. Because data alone is not enough. If everything meets the required standards, the batch is approved. Now it moves to packaging. The toothpaste is transferred to automated filling lines. Tubes move rapidly through the system. Each tube is filled with a precise amount, not slightly more, not slightly less. Then comes sealing. Heat is applied to close the tube. This creates an airtight barrier that protects the product from contamination. Heat appears again here, just as it did earlier in the process. Each tube is marked with batch information. This allows full traceability. Manufacturers can track every tube from production to retail shelf. If an issue arises, it can identify exactly which batches are affected. Even after packaging, the process does not stop. Samples are taken again, tested again. Storage conditions are monitored. Distribution is tracked in real time. Every tube becomes part of a larger system. There are also constant efforts to improve efficiency. Production lines run continuously, but they are not perfect. A new mixing machine might introduce unexpected downtime. Data reveals patterns. Maybe output drops during certain shifts. Engineers analyze the system. Sometimes a small adjustment makes a big difference. Rerouting glycerin flow to a different manifold might increase throughput by 10%. Adjusting pressure might stabilize mixing. This is not a static process. It evolves constantly. And then, after all of that, the toothpaste leaves the factory. It moves through distribution networks, across regions, across continents. Eventually, it ends up in your bathroom. A simple tube, used twice a day. But behind that simplicity is a process built on precision. Numbers, measurements, verification. Because if even one detail is wrong, you would notice. Maybe not immediately, but over time, you would. And that is exactly what this entire system is designed to prevent.